Motion is defined as an act, process, or instance of changing place. So think about what motion looked like to you. And today we are going to discuss different ways we can define motion. So, first off, we're starting with position, where you are. And position is kind of relative. So, you could say you're on planet Earth, you're in the United States, Virginia, Richmond, you're at school, you can be in the academic building. There are many answers to the question of where are you? Now, what's really important is considering how your position changes. That's way more important than just where you are. But also describe about how it changes. So here on campus, you can see the dot is the gym. You have the track, softball field down to the left. You have the field hockey field, baseball field. It's a pretty big campus. All right, so really motion is about changing where you are. So changing your position. And the two words we'll use to describe position or change in position are distance and displacement. Distance is simply the total length of the path taken. Displacement is very similar, but it's the straight line distance and direction from where you start to where you finish. So if I were to travel like this, I could go anywhere. My distance traveled, I'd have to measure that entire red line. However, my displacement would be from where I start to where I finish in a straight line. So my displacement would only be from here to there. It would be the length of that line. Both distance and displacement are measured with a meter, which we should already know that because the meter is the SI unit for length. Now, displacement also has a direction attached to it because which way you go is very important. So you can think about north and south, east and west, up, down, left, right, all of those different types of directions. So for an example, how far away is Chesterfield Town Center? So we are up here at Trinity Episcopal School, and Chesterfield Town Center is right over here. And the question is, how far away is it? Depending on how you think about this question, there can be multiple answers. Part of it depends on the route that I take. So one route that I can come out down Cherokee, down Old Gun, cut out here. I can cut down and around. That is one path that I can take. I could also take another path that goes out here, around. I could go down Huguenot. I could come around that way. There are many options. So the answer is it depends. The route that you see in blue is 4.3 miles, and it takes about 9 to 14 minutes to get there. But if I could walk in a straight line from school to Chesterfield Town Center, then I could get there with a much shorter distance. So the distance depends on the route, 4.3 miles for the blue one, but my displacement, the straight line distance from where I start to where I finish, well, it's less than 3 miles away, and it's in the south-southwest direction. All right, so here are some examples. Example one, I have an Olympic swimming pool that's 50 meters long. We're going to look at the distance and displacement as the swimmer completes a 200-meter race, which is 4 lengths of the pool. All right, so at the start, she hasn't swam anywhere yet. So her distance and displacement are 0. During the first lap, she's going to go all the way down to the other side, which is 50 meters away. And her displacement from where she started to where she finished is also going to be 50 meters. Now on the second length, when she goes from the top back to the bottom, that's another 50 meters. So she has traveled a total of 100 meters, but her displacement, the distance from where she started to where she finished in a straight line, is going to be 0. It's because she's back where she started, her displacement is 0. All right, for length 3, she's going to go back the length of the pool. That's going to add another 50 meters, so we're at 150 meters. She's 50 meters away from where she started. And the last lap, we can get up to 200 meters total. And her displacement is going to be back to 0. Here's another example around a track. So one lap around the track is 400 meters. So we're going to look at the distance and displacement as the runner completes a 1,600 meter race. So at the start, the runner has not ran. So the distance and displacement are 0. Let's say they start right here. After one lap, they have traveled 400 meters, but they've arrived back at the starting line, so their displacement is 0. After another lap, the runner has traveled 800 meters, but they're back where they started. After the third lap, they're going to be at 1,200 meters. They're still back at where they started. And by the end of the fourth lap, they will have ran 1,600 meters, but they finished where they started, so their displacement is 0. Now, I could also consider other lap lengths. So let's say she ran a 200. A 200 would be half a lap. So if our runner starts here and runs half a lap, the runner will finish here. So for a 200 meter race, the distance would be 200 meters, but the displacement is the straight line distance and direction from where they start to where they finish. So this arrow shows the displacement of the runner that starts here and runs a 200 meter race and finishes there. All right, and a third example. Someone on the team left trash on the bus, and the whole team had to run. We're going to find the distance and displacement. They start on the left end line, ran to the 20-yard line and back, the 40-yard line and back, the other 40-yard line and back, the other 20-yard line and back, and then a final run to the right end line. So for Sandy's sake, this is what the path looks like. You're going to start on the end line and go out to the 20 and back, out to the 40 and back, the other 40, the other 20, and then they're going to finish on the far end line. And the question is, what's the distance and what's the displacement? So first we'll do the distance. Well, 20 yards out and 20 yards back, so that's 20 times 2. I'm going to do 40 yards out and 40 yards back. And then to get to the other 40, that's going to be a 60-yard dash. twice, then 80 yards twice, and then finally 100. And if I add all of this up, I will get a 500 yard distance. How about my displacement? My displacement is the distance and direction from where I start to where I finish in a straight line. I'm starting here. I'm going to finish there. So my displacement will be 100 yards to the right. All right, now for a black diamond example. We don't always just travel in one direction. Sometimes we can travel in two directions. So in this case, I have Amanda walking 3 kilometers west and 4 kilometers north. So Amanda starting here is going to walk 3 kilometers west and then 4 kilometers north, and she's going to finish right here. Find the distance traveled and the displacement. All right, the distance, we just add it up. And that part's done. But the displacement is a little different. So the displacement is going to be the hypotenuse of our triangle. Remember our good friend Pythagoras? A squared plus b squared is equal to c squared. So I have 3 squared plus 4 squared is equal to c squared. That's 9 plus 16. And if I take the square root, I get 5 kilometers. So the distance from where she started to where she finished is only 5 kilometers away. But I also need a direction. The direction in this case you can state as an angle. In physics, an angle is shown by this Greek letter theta. Kind of looks like a cursive O. So that is the symbol for an angle. And from geometry or trigonometry, we know tangent of theta is opposite over adjacent. So the opposite is 4, and the adjacent is 3. So if I take the inverse tangent of 4/3, then I can get my angle. You have to make sure your calculator is in degree mode. If I take the inverse tangent of 4/3, I get that my angle is 53 degrees. So the total answer for the displacement is 5 kilometers, 53 degrees north of west. I like that range. Okay. So first part about motion is about changing my position. That's my distance or displacement. Next up is how quickly my position changes, and that can be defined with speed and velocity. There are multiple ways that you can define how quickly your position changes. We can talk about averages, which is looking at the entire time of travel, or we can look at instantaneous which is how fast you're going at a single time. These definitions all seem very similar, so let's break them down. The average speed is the total distance traveled divided by the time it takes. And we have an equation here. Speed is distance divided by time. Instantaneous speed is how fast an object is moving at a moment in time. So it's like what your speedometer says on your car. Average velocity is different from speed because it looks at your total displacement divided by the time it takes. So your average velocity is equal to your displacement divided by time. And your instantaneous velocity is the same as your instantaneous speed, but with a direction. So instantaneous speed and velocity are the same, except for velocity always has a direction. All right, the SI unit for speed and velocity is meters per second. This is important to remember. Now, how do we get that? Well, speed is distance divided by time. Distance is measured in meters, and time is measured in seconds. So in the equation itself, I can see that speed is measured in meters per second. So we can go back to Chesterfield Town Center from school. And the question is, what is the average speed from the time you leave school until you get to Chesterfield Town Center? For that, we just take the distance and divide by the time. So the distance traveled is 4.3 miles. And let's say what's your fastest average speed? That'll be when it only takes 9 minutes. It's about half a mile per minute, which is about 30 miles per hour. Now, you are not actually driving 30 miles per hour this entire time. We have stop signs, we have to speed up, we have to slow down. Parts of this route have a speed limit of 45 miles per hour. But when you average all of that together, you get an average speed of 30 miles per hour. Now, the average velocity is displacement divided by time. So the displacement in a straight line is shown here on the picture, 2.97 divided by 9 minutes. And for that one, you get 0.33 miles per minute. Which is about equal to 20 miles per hour. So if you could travel in a straight line, then your average velocity would only be 20 miles per hour. And let's say southwest. You could go slower and get there in the same amount of time as somebody who takes the route that's shown. When you zigzag back and forth, you have to travel faster than somebody that can travel in a straight line if you're going to get there at the same time. All right, here's some more. You're going to the beach on I-64. If it's 100 miles and you want to get there in 2 hours, what is your average velocity? All right, so average velocity, displacement divided by time. So my displacement is 100 miles, but remember, displacement needs a direction. Which way is Virginia Beach? Let's say it's to the east. And my time is going to be 2 hours. So V is equal to 100 miles east. I divide by 2 hours, and I get that it's 50 miles per hour to the east. If I were to drive 50 miles per hour towards the west, I'd end up in the mountains. So direction is important. All right, let's say you immediately get to the beach, but you turn around and come home, but there's a backup at the tunnel, like there usually is, and it takes you 3 hours to get home. What is your average speed for the entire trip? Entire trip, I'm looking for the average speed. Average speed is distance divided by time. So if you start at school and you drive all the way to the beach, it's 100 miles. And it took 2 hours. And you drive all the way back. It's 100 miles that way. And it took 3 hours. The average speed is going to be 200 miles over 5 hours, which is hopefully 40 miles per hour. Now, your average velocity is your displacement divided by time. So if you start here and you finish here, your displacement is 0. So your average velocity is 0. You could think of this in a little bit of a different way. You could think that all velocities towards the east are positive and velocities towards the west are negative. And what you'll get is that these two velocities will cancel out. And that's why your average velocity is 0, even though you were moving the whole time. All right, and that brings us to how quickly velocity changes, which is defined as acceleration. Acceleration is in the equation. It says it's equal to the change in velocity over time. All right, so velocity is measured in meters per second. And I'm going to divide by seconds for time. So I can rewrite this as meters per second, or meters per second squared. So the SI unit for acceleration is meters per second squared. This is not a formula, it is the unit for acceleration. All changes in velocity are defined as acceleration. It's a little pet peeve of mine, but the word deceleration is normally used to mean slowing down. But you can just say it's a type of acceleration because slowing down is a type of change in velocity. All right, velocity is like speed with direction. So if I am going to change my velocity, I can either change my speed by speeding up or slowing down, or I can change my direction by turning. What controls on a car can cause you to accelerate? Yep, there's my car. Okay, we gotta get some headlights going. Woo, woo, woo. Windshield. Here's my handle. Oh, little tailpipe. Doing a spoiler, probably. Spoiler alert. All right, beautiful. There's my car. If my car is going to accelerate, the gas can help me speed up. The brake causes me to slow down. Whoa. And steering wheel can cause me to change direction. So all three are accelerators on a car. All right, the Tesla Model S can accelerate from 0 to 97 kilometers per hour in 2.28 seconds. What is the acceleration in meters per second squared? All right, so let's notice a few things here. My velocity is given in kilometers per hour. My time is given in seconds, and I want my acceleration in meters per second squared. So step one, I need to convert. So 97 kilometers per hour. I need to go to meters per second. So I'm going to get rid of kilometers and go to meters. There are 1,000 meters in a kilometer. And I want to get rid of hours and go to seconds. 1 hour is 3,600 seconds. So if I take 97, multiply by 1,000, and divide by 3,600, I get that the speed in meters per second is 26.94 meters per second. All right, my acceleration is equal to my change in velocity over time. Whoa, 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 time out. That's a triangle. That triangle is called a delta. It's a Greek letter. And it means change. So my acceleration is my change in velocity over time. My velocity went from 0 to 26.94 meters per second. So my change is just going to be my final velocity, and then I divide by the time it takes. If I divide by 2.28, I get that my acceleration is 11.8 meters per second squared. This acceleration is greater than the acceleration due to gravity. So you would feel like you're being pushed back into the seat as you're accelerating in this car. All right, another example with gravity. When an object is falling and no other forces are acting on it, that type of motion is called free fall. So free fall is when only gravity is acting on an object. On Earth, the acceleration is 9.8 meters per second squared. So my acceleration is 9.8 meters per second squared. How fast? I'm looking for a velocity. Will an object be moving after it has fallen for 10 seconds? That's my time. A is equal to my change in velocity over time. So I have 9.8 is equal to my change in velocity over time, which is 10 seconds. If I need to get my change in velocity all by itself, I have to multiply both sides by 10. So my change in velocity is equal to 98 meters per second. 98 meters per second is very fast. So think about something that actually takes 10 seconds to fall. It's a very long time. So as something's accelerating, it's getting faster and faster and faster. It's going to cover more distance over that time. All right, how about displacement with acceleration? So this is a black diamond concept. Like I just said, as something is accelerating, its velocity will continue to change. So the distance it covers over that time period will also change. So when something is accelerating, the distance it travels is given as 1/2 times the acceleration times the time squared, where d is equal to 1/2 at squared. This is because as I'm accelerating, my velocity is changing. So how far will the mic fall if it is dropped and allowed to fall for just 2 seconds? Well, the distance is equal to 1/2 times the acceleration times time squared. It's 1/2 times 9.8 times 2 squared. So that's 1/2 times 9.8 times 4. This gives me 19.6 meters. So nearly 20 meters is the distance something will fall in 2 seconds. All right, so in summary, motion is when you change your position. I can discuss a change in position as being either distance or displacement, how quickly my position changes with speed and velocity, and how quickly my speed changes with acceleration. So the things where I can ignore the direction I travel are distance and speed. Displacement, velocity, and acceleration all have direction included. So this is a key concept in physics. We can have measurements, some include direction, some don't. Any measurement that does not include direction is defined as a scalar. So distance and speed are both scalar measurements. They do not have direction. Time, color, mass, all of those are scalars. Now, a vector is any measurement that requires a direction. So we have displacement, velocity, acceleration, a force can be a vector, momentum, there are some other measurements that we'll go through as we progress through, but this is a good start. All right, so a vector is anything that includes a direction. The math gets a little different sometimes when we deal with vectors compared to scalars. For right now, if you can remember this box, you will be good to go. Thank you for following along, and I will see you next time.